Right, I'm going to do two parts for this particular exercise. Just the first part would be just these questions, and I'm going to start by reviewing, idea of parallelism, parallelism of vector. So say you have a vector u, and it looks something like this, right? And the vector v probably shorter or something like that. And if they are parallel, then we can then say u is equivalent to v. Of course, that's not true. So to make them be equal in the sense, we write u as a multiple of v. Of course, in this case, the k is scalar. And of course, basically, we just say that it is a real number. And k can be anything. It could be -2, could be 1/5, and it could be just 6, right? So if it's parallel, you can write a vector in this form. And if you say that now we define the vector differently this way, AB, and it's another vector PQ, right? And using 2 points to form a vector. And if they're parallel, then we can then write this is equal to, say, this is not k, no problem, PQ. And obviously they're parallel if it is geometrically shown they're parallel. But we do not know, because since they do not have a common points, A, B, PQ, they are not common. There are no common points, and so we're not sure whether they are on the same line. And the other thing is the idea of collinearity, and so I close this place. So very similar. Well, actually, it basically is just parallelism. However, there's one major difference, and that difference is, suppose we have 3 points A, B, C, and they can be connected by a straight line, whether in 2D plane or 3D space, right? And if we can then show that AB is equivalent to KAC, or as long as there's a common point, I choose A as a common point. You can start with this. You can show that KA is equivalent to say K1, some scalar, BC. Right, so there's a common point. The first one, the common point is A, and the second one, the common point is B. You can use C as a common point too. There's no real restriction there. But as long as there is a common point, and you can write both vectors, relate them as follow, then you say that A, B, C are collinear. And this is the concept of collinearity. Now, how I'm going to use these both concepts, especially the second one, to do these first questions. Look at this. This requires some drawing. Let me start by this. I choose A as a common point, and so I want to find AB. I'm going to jump ahead and just give you AB 6 to -4, right? And it is I can actually, it's a common factor, so I factored it 2, so you get 3, 1, -2. And how about AC? Just jump ahead and give you it. That would be equivalent to AC, OC minus OA, right? And so I'll actually get 21 7th, and then also -14. And it's a common factor, apparently, is 7, right? And you get 3, 1, and -2. And you notice that they actually have same, multiple of some vector, same 3, 1, -2, 2, -2 here. It means that, in other words, I can then say AB is actually 2, 3, 1, -2, and I can then now divide by 7, but to do so I times 7 to balance the whole thing out. It's 7 and minus 14, right? And however, this is actually equivalent to AC, and then therefore we can say that A, B, C are collinear. Prove that we have shown that the vector A, B is a multiple of AC, and they are collinear. Right. I will skip the second part. Probably look at something because there's a question very similar to that later.